last lesson, we made all the necessary preparations to consider the quantum Shor's factorization algorithm. Let's recall that we have a composite number m, which is the product of unknown primes p and q, and our task is to find these numbers. At the same time, we'll show that the factorization problem can be reduced to calculating a period or order r for some function ym of x. So, at the input of the switching circuit that implements the Shor algorithm, two L qubits in the state 0 are entered. Moreover, the first L qubits form the data register and the next L qubits form the value register. At the first stage of the Shor algorithm, using Hadamard transform of the data register, we create an equiprobable superposition of all possible states of these qubits. Since the data register in this case is responsible for the value of the argument x of the ym function, then in fact, as in the Deutsch-Jozsa algorithm, we run through all possible values of the argument x from 0 to n-1. The second register remains unchanged. The result is a well-known state representing the sum of x from 0 to n-1, state x tensor multiplied by the initial state of the data register, taken with the normalization factor 1 divided by the square root of n. Further, the register of values for each term for the resulting superposition are filled with the values of the function ym from x. As a result, we obtain the normalized sum of x from 0 to n-1, state x tensorally multiplied by the state ym of x. To better understand what we have just done, let's consider an example for m equals 15 and the number a equal to 2. That is, when the function ym of x is equal to the remainder of dividing 15 by 2 to the power of x. As a result, as we see on the slide, we establish correlations between the terms of the resulting superposition. That is, the values of the second register begin to repeat. If we continue to write the terms of the superposition further, we will see that the values of the second register can take only one of four values, 1, 2, 4, and 8. In particular, it is clear that since there are four different values, the period of the function ym in our case is equal to 4. In practice, we cannot know that for sure, since we cannot measure the entire superposition, so we will continue to consider the algorithm. Next, we want to measure the register of values in the measurement basis, and the data register is still unmeasured. As a result, we obtain an equiprobable superposition of 2, 6, 10, and etc. multiplied by state 4 in the height register, which can be expressed as a normalized sum over j from 0 to n divided by r-1, state r multiplied by g plus 1 tensor multiplied by the state 4 of the second register. Moreover, j is the zero term of the resulting increasing arithmetic progression, and in our case it equals to 2. Thus, the second register is used to prepare periodic superposition of the first one. In fact, here, as in the Deutsch algorithm, we use quantum parallelism. Now we can find the period r using the Fourier transform. As a result, we obtain the sum of k from 0 to n-1, fl of k multiplied by the state k. Here, fl of k is the probability amplitude that determine with what probability pk, the state k, will be obtained when measuring on the first register. The expression for the probability pk will not depend on f, while the greatest contribution to it will be made by those terms whose rk divided by n is close to an integer, or rather the remainder of dividing rk by n is in the range from minus r½ to r². If the ratio of r to n is small, then it can be obtained that k with probability 4 divided by pi to the power of 2 will take discrete values. That is, after the quantum Fourier transform, we obtain an equiprobable superposition with period n divided by r. Further, the probability measurement makes it possible to determine the values of k equal to nu multiplied by n divided by r, where nu runs through integer values from 0 to r minus 1. Then, if the ratios of r to k and k equal to nu multiplied by n divided by r are known, you can find the ratio of nu to r. Then, by transforming this relation to an irreducible form, determine the period r. And at the end, now in the period, use the classical Euclidean algorithm. As you can see, this algorithm is quite non-trivial. Therefore, in order to better understand what is happening, consider an example. Now, let's take a closer look at the factorization algorithm for example, m equals 15. First of all, we should take the prime number that has no common divisors with m. For example, let this number equal 7. Now, find the order of function y15. To do that, we should start with the quantum state of 22 qubits as 11 qubits in the first register and also 11 qubits, for example 11, of course, in the second register, and perform the Hadamard transform over this state. So, after the Hadamard transform, we obtain the following state: 1 divided by square root of 2 to the power of 11, sum of the x from 0 to 2 to the power of 11 minus 1, x, and the state 0. So we could write out the explicit form: 1 divided by square root of 2 to the power of 11, to the state 0 plus state 1 plus etc. plus the state 2 to the power 11 minus 1 multiplied by the state 0. Secondly, we should record the y15 of x function in the second register. So now our quantum state is 1 divided by 2 square root of 2 to the power of 11, sum x from 0 to 2 to the power of 11 minus 1, x, and here we have the y15 of x function, which equal to 7 to the power of x modulo 15. We could calculate the y of x function and write down the following: 1 divided by 2 square root of 2 to the power of 11, state 0 to the state 1 plus state 1 to the state 2 plus state 2 to the state 4 plus 3 multiplied by 13 plus 4 multiplied by 1 plus 5 multiplied by 2, and etc. These numbers are just remainders of dividing the 7 to the power of x by the 15. And one can see that there is a period in this function, and after the 13, the sequence is start to be the same as for first 4 terms. The next step, the value register is being measured, and after the measurement, we get one of these these 4 values. For example, let it be the value 4. So perform the inverse QFT to the data register. We could write down the state of the system after the measurement as 4 to the 2 to the power of 11, 2 plus 6 plus 10 plus 14, etc. And we want to perform the inverse QFT and obtain the following expression, somewhere with the k from 0 to 2 to the power of 11 minus 1, f from k on the state k. Here the f of k is the probability amplitude for state k. And it turns out that only 4 values of k, k1, k2, k3, and k4 are presented in this sum, and all other are equal to 0 due to the quantum interference. And it's the values of k equals 0, 512, 1024, and 1536. Let, for example, the key be 100 or 1536. Now we can calculate the ratio of k to the 2 to the power of t. It's 1536 over the 248. And this is just 3 divided by 4. And taking into account that k equals to nu n by the r, we can find that k to the n equals to k to the 2 to the power of t and equals to nu to the r. And this is just 3 divided by 4. And from this expression, we can say that r equals to 4. As a result, we obtain the period of a function f. Now, let's write down the following expression. 7 to the power of r in half, it's 2, minus 1, and 7 to the power of 2 plus 1 being divided by 15 had a remainder of 0. And after performing the classical Euclidean algorithm, we can obtain that the greater common divisor of the 48 and 15, the 48 is actually the first factor, equals to 3, and the greater common divisor of 15, it is the second factor, equals to 5. Thus, m equals 15 equals to 3.5, and 3 and 5 is the prime numbers, so we just factorize the number m. In conclusion, we know that the Shor factorization algorithm gives an exponential gain in speed in comparison with the classical factorization algorithms. In our course, we did not understand the issues related to the theory of the complexity of algorithms. However, it can be argued that all the algorithms we considered give a significant increase in performance compared to the classical ones. This makes them interesting for practical use. That's all for now. Thanks for your attention.